Okay, so our final speaker this afternoon is Joseph Slawny.
Thank you. And I wanted to present, to talk about zeros of some system. I am I have on and off love affair with this kind of systems for a while. And I want to discuss conjecture about zeros of partition function for the systems. And here is typical result of numerical calculations using Mathematica. Here are two circles. I'll call them F circles.
They are circles.
They are circles. They are deformed. If you look at the scale is different.
Right.
And it's nicer like this. So there are two circles centered at 1 and -1, and of the radius square root of 2. And I want to discuss two different kinds of systems which have zero distributed on this kind of circles, mostly according simulations. One kind of system is comes from statistical mechanics, and the other from theory of linear codes. So let me first discuss the statistical mechanics systems. This is what I want to do here, discuss the zeros, this spin 1/2 ferromagnetic systems that have this kind of zeros. Now, duality will be very important in defining the systems. And then I want to discuss relation with classical binary codes. With lattices associated with these codes that I hope will help me to solve the riddle, and with theta function defined by these lattices. So the notation was set up. I will use the notation that Roberto was using 2 days ago. Here is the Hamiltonian of the system. So at each point of the lattice, I have a variable sigma A. A is the point of the lattice. The lattice will be simple lattice ZD. And sigma, if B is subset of the lattice, then sigma B is the product of the sigmas, and the Hamiltonian is just sum of those. That's a formal expression. I'll consider later final subsystems, but the sums will be not formal. These are the coupling constants, assumed positive, but in most of the what I am going to talk about, that doesn't matter. I'll consider both univariate case when all these coupling constants are equal, and multivariate case when they are different. Here are two examples of the models. Let me first go to this one. How is it visible? Yeah, it's visible. Is there a pointer here?
Pointer's in the corner over there.
Oh, thank you. So this is a model, triangular 3-spin model. It was solved by Baxter and Wu, and this is the lattice, 2-dimensional lattice, and the bonds over which we take product is this are triangles. So there are two triangles. Let's pick up these two, and the other triangles all over this plane are translations of these two. So I would say that in this case I have two generating bonds, because everybody is a translation. How does this work? Doesn't have much. Another model, I'll have just 3 models. The simulations I run on many more than that. The other model is also has been solved, is the Ising model. So here are the two bonds. I am not drawing the lattice anymore. So one bond would be here, another here, and all the others would be translates of these two. And one more. Here is what I call 6 model, for obvious reason that these two generating bonds are like number 6. Okay, just to refer to them. Okay, so what we are going to consider, we are going to consider a partition function now for finite system. I'll take, so the Hamiltonian in the finite subset lambda of the lattice is minus the sum, and that's our partition function. I'll take always finite system with periodic boundary conditions or toroidal boundary conditions. So they are glued at the end, and usually lambda will be rectangle or parallelepiped of different size. And as we were told quite a few times, in statistical mechanics one considers thermodynamic limit. So take log of this partition function, this expression, and go with lambda to infinity and over reasonable lambdas. And the problem that is important is location of singularities of this pressure as a function of parameters that enter the Hamiltonian. If you have singularity, we know that something is strange there, most likely phase transition takes place. So we want to know the location of singularities. Now I want to go to the duality property. So the main result for Ising model around 41 runs as follows. Suppose that we replace the coupling constants of Ising model, 2 coupling constants, the rest are the same, one horizontal, one vertical. Suppose that we replace this coupling constant by another pair related by these relations. Then we know that the duality transformation tell us that duality relation tell us that we have this identity. Okay, so how this was, and first it was proved by using transfer matrix. What do we get out of it? What was obtained, and quite spectacular at this point, that was the first rigorous result about the Ising model. If we know, if we set the coupling constant equal, then the fixed point of the transformation, which is this and this, what we know, if there is one singularity, then the singularity has to be at this point. And that was something spectacular at this point, because that was first exact result. There are many exact results, approximate results, and that was a result that really contradicted all the approximations. Okay, I want to draw attention to the fact that the duality transformation interchanges here the horizontal and vertical. The coupling constant for horizontal, let's say, is related to vertical here. Now, now I want to formulate. So let me give away one secret, that this location of 0 onto the circles that I want to conjecture is quite common, is related to the property of the system being self-dual. So I want to describe self-dual systems. Okay, this multi-spin self-dual system. So let me take finite set. Again, think about torus in any dimension, not necessarily 2 dimensions. Consider configuration space, and then 2 maps. So we have our family of bonds now on the torus. And for each configuration, consider those bonds for which the product is equal -1. So in the language of ferromagnetic system, that would be that this plaquette or this bond is excited in a way. +1 is the lowest energy, -1 is excited, and capital gamma will be the image of this. So in case of easy model, usually you draw a line crossing the excited bonds. So it would be the what's called contours. And then another family of these families of bonds, namely for any configuration. Let's see. Right.
For all configured. You have a quantifier, yeah.
Right. Consider a family of, so this script K would be a family of bonds belongs to script K if for any configuration the product of bonds over each product of the sigmas over each bond in B is equal 0. So for example, in Ising model, we will have little squares would belong to B. And here is example for this Baxter-Wu model. If you take these 6 bonds, then you can easily see that each bond of the lattice belongs to 2 bonds. This one belongs to these 2 bonds, and so on. So this is element of K. Okay. Yes.
In the Hamer's derivation, the critical point, so he established an isomorphism between flip spins in the low temperature expansion and the contours in the high temperature expansion.
Right.
So your contours are your gammas?
No. So
These gammas are Pyrrhus contours.
are
They're
Pyrrhus
sets of- they're
contours.
sets of unsatisfied
Right.
bonds.
Are the Pyrrhus contours. So they are, in this case, separate points that have different sign of spin. Right. And then another quantity that's important, namely the ground states. Ground states are simply those configurations for which, so ground states are configurations for which, for each bond, we have the product equal to 1. So in case of Ising model, there are 2 ground states, plus and minus. And for the Baxter-Wu model, I'll show in a moment the ground state. There are 4 ground states for the Baxter-Wu model. So duality now is formulated in terms of 2 expansions, comparing 2 expansions for partition function. One expansion is expansion about the ground state, any ground state, and runs as follows. That's our partition function. Subtract the value of each of those at the ground state, and then this is equal -2 when sigma b is -1 and 0 otherwise. So we are getting this factor. So if we pull out this and take advantage of the symmetry, we are getting the following expression. An interesting factor, and the main part is here. Sum over all these contours and product over for each contour. And similar way, if we use the fact that sigma b squared is 1, we are getting this expansion, non-interesting factor, and here sum over cycles, elements of K cycles, alcohol, and here again product. Okay? And this is low temperature expansion because K is proportional to temperature, to inverse temperature. So at low temperature, this is small, and at high temperature, this will be small. So high temperature, low temperature expansion. And now duality is obtained in the following way. You just want to map terms of this sum onto terms of this sum. So system is self-dual. I'll talk only about self-dual models. The duality works more generally. One can define two systems being in duality, but I want to consider only self-dual model. So a model is self-dual if we can map the contours on the cycles in there is isomorphism between these two sets. Okay? I am here not very precise, but anyway, I don't want to prove anything here. I want to just formulate the concept. Okay. So now these are our main actors. These two polynomials, one coming from high temperature. So when we substitute for W this exponential, we are getting this interesting part of partition function. And for X, the tangent hyperbolicus, we are getting this high temperature expansion. Okay? And for self-dual system, these two quantities will be the same. So what kind of systems are self-dual? Well, first, to get a good map between the system, we consider it's standard to consider the group structure. First, on the set of all subsets of bonds, which is here symmetric difference, which is the same isomorphic to taking just two-element field and taking to the right power b. Okay, so functions from b to 0, 1 are identified with subsets of b. Okay, so gamma and k will be subsets of this, and it's easy to see that in fact these are subgroups. Subgroups of also, if you want vector subspaces of this vector space, vector subspaces over Fb. Okay? So we have now the following: the gamma that was defining the groups is a homomorphism. S is kernel of this homomorphism, and gamma is the image of homomorphism. And K is defined somewhat in a way, in dual way. I'll come back a little bit more to relation between K and gamma later. Anyway, but let's now adopt the definition. System is self-dual if there is a bijection of the set of bonds on itself, such that the which commutes or anti-commutes with translations. Okay? The system has built-in translation invariance. So we want this map commute or anti-commutes means that, let's say, tau. So suppose that we map bond B on bond B star. So we want that tau A B is equal tau minus A star is equal to this. So then I will say that anti-commute. And I would have to talk quite a bit more to explain why the anti-commuting is important. Okay? But so in fact, when you look at this, usually it is, yes?
Right, it's a little bit abstract. Right? In other words, let's say you take not just a 3-spin interaction on faces of the triangular lattice, but consider others like a 4-spin interaction on the faces of the square lattice. In other words, what is the general class of multi-spin interactions that this would apply to?
Well, there is a theorem here. Which systems are self-dual? Is this your question? Which systems are self-dual?
I mean, the square lattice is self-dual, yeah, but with a 4-spin
well,
interaction.
square,
It's not solvable.
you have to specify the bonds, yes, to talk about self-duality.
Bonds along the edges of the square.
Or you mean Ising model?
Four-spin interaction, like the back.
Four spin and
He's
what?
using the word bond to what you're saying is interaction. So when you say four-spin interaction, he's
Four-spin
saying
bond.
a bond is a plaquette. And he's going to give a theorem about which multi-spin Ising models are self-dual.
Does this answer your question?
Yes, that's
Okay. So here is this general theorem that a system is self-dual and can be in any dimension if and only if has two generating bonds. So for example, Ising model is self-dual, but if you would take this two Ising bond and add set bond, triangle to this, model would be not self-dual. Okay? So we have plenty of self-dual models, but some self-dual models are more self-dual than others. For example, in Ising model, it's self-dual, but the contours and the cycles are different creatures. Contours, so typical, for example, a contour, if you have just one you flip one spin, here is minus and the other are pluses, then you are getting this as a contour. Okay? On the other hand, the cycles are closed curves. So they are isomorphic in a way. You can map one to another, but they are different. Okay? Some models are self-dual in stronger sense, in the sense that the set of cycles is the same as the sense of as the set of contours. So, for example, let me go back to my this triangle model. Here, this fellow, this element of P of B, is a both cycle and contour, because it's obtained by flipping the central spin, and all others are +1. Then you are getting this 6 bonds, and also you can see that it's cycle. Okay? So which models are strongly self-dual? I'll call them. Where I am here. A model is self-dual if and only if, well, first of all, it has to be two-bond system, and then one bond has to be obtained by inversion of the other bond. Okay? So, for example, this triangular model or the 6 model was also strongly self-dual. This model is also strongly self-dual because you see that this bond is obtained from this one by this inversion. Okay? And it appears that any model with this kind of two bonds is self-dual. So, for example, if you take 3 dimensions, take a model in which you take one bond is tetrahedron and the other is the flipped tetrahedron, then this model will be strongly self-dual. And of course, there are infinite number of the strongly self-dual models. I am here lying a little bit because there is algebra lurking behind this, and there is some unique factorization domain behind this, and one has first to factorize the bonds and remove the greatest common divisor of the bonds. But once let me see. So I am essentially out of time. Yes.
No, you have 5 more minutes.
5 more minutes. Well, I can advertise at least. And so perhaps let me go. Let's see. Okay. Now, so let's take final system with periodic boundary conditions. We were talking really about duality of infinite system. Now, when such system is self-dual, little calculation with dimensions show that, well, first we have this ground states for infinite system. This is the model with the Baxter-Wu model, and here I am drawing +1 by, replacing by circle, -1 by this axis, and this would be one of the ground states. Okay. Well, trust me. Okay.
Where are the triangles?
Bill Gates has made it difficult to see the triangle.
Well, the triangles are a little bit above, but I am not showing the triangles. I am showing now the configurations. Okay? You have to trust me that these are the ground state configuration. Here are the bonds. Okay? But, okay, take, for example, triangle going through these three points. So you see they have 2 minuses and 1 plus. Okay? And if you continue, you'll see that in each triangle, the lattice consists of the centers of the square. Okay? So one bond would be like this. You see 2 minuses, 1 plus. Okay? Another was, I don't remember. Well, one was like this, another one this. Again, 2 minuses, 1 plus. Okay? So all over you have the situation. Let's now take 3 by 3 system with periodic boundary conditions. Okay? So you see that, for example, when this fellow is really connected to this fellow. So this has to be identified with this, and you see that this ground states project to ground states of the 3 by 3 system with periodic boundary condition. On the other hand, if you take 4 by 4, this fellow is connected to this one, but here next to it is -1, and this is +1, so the ground state doesn't project to the periodic system. So it appears that it's quite easy that the system is self-dual with periodic boundary condition if and only if the number of ground states is 1 that project to this periodic boundary condition. So for example, this fellow, if you take 1, 2, 3, 4 by 4, would be self-dual. Okay? And the conjecture is now that if you take any system with periodic boundary, finite system with periodic boundary condition of this strongly self-dual type, then when you look at the partition function, it has 0 on these 2 circles. Okay? So we know this for Ising model, but we know it really in thermodynamic limit or with very contract periodic boundary conditions that are not periodic.
Right, the Bracon code.
Right. Whereas for these models, periodic boundary conditions have, and so you have infinite number of models for which I conjecture that this holds, but there is strong relation also with these codes. These are in fact, these are codes in sense of coding theory, and
So you have a generalization of the Bracon boundary conditions, for example, for Baxter-Wu. Is that
no.
first?
Well, here I just take for those models just periodic boundary conditions. There is no need for any twisting. Okay.
And then you find that the zeros lie exactly on these
Apart
circles.
from time to time, I'm getting 1 0 off. 1 0 off. And well, there is. I have much more information about these polynomials that appears and about the zeros. Part of this is rigorous and part based on calculation. But I wonder if anybody. I googled if there are results about these polynomials correspond to what in coding theory is called weight enumerator. Exactly, they are weight enumerators corresponding code. But I didn't find any result about zeros of the weight enumerators. People look usually at the first power apart from 1. This is important quantity encoding, but not 0. When I run this on the classical cyclic code, I'm getting also zeros on these two circles. So well, there is something here, perhaps. Okay, thank you. Yes.
But the duality relation gives you some mapping between zeros of one.
Right. So the set of 0 is invariant under transformation x going to 1 minus x, 1 plus x. And these two circles are invariant under this. Okay, and so they give you...
But there are other geometries that are invariant under this. No?
Sure, sure. But, you know, when you map the 0, when you use theta function, which I didn't describe, then in the upper half plane, you are getting that the 0 are on geodesics, on few geodesics. And this is tantalizing. They are on these semicircles emanating from few points. Okay, so perhaps there is something to it.
Okay, let's thank the speaker again.